Hello, this is John, and this is a re-recording of the three-phase method in a series going through daylighting simulations using matrix-based method. I had previously recorded this three-phase, but for some reason there was a sound issue, and someone kindly pointed out to me that the sound was cutting out on the old recording. So thank you very much. It was Alex who pointed that out. Thank you very much, Alex. And let me re-put myself. So it's maybe a tiny bit disjointed, but I'll do my best. I would imagine previously I discussed the two-phase method, and I would have talked about how it's the two-phase or the daylight coefficient method is about the direct transfer from the sun and the sky through the fenestration into your point of interest, which may be a camera view or it may be calculation points. And the important thing to note is it happens in one calc from the sky straight to the points. The difference with the three-phase method is that the calculations are separated into three parts, hence three-phase. Two-phase is the sky and your points. Three-phase is the sky, the transfer of light energy from the sky to your windows through phase one, through your window fenestration, phase two, from your window fenestration to your either camera view or your calculation points. So one, two, three. So how does that actually happen? Well, it's you do one calc, and there's imagine a sampling hemisphere is placed on the window, and it looks out. I'm using how am I even looking at this? Oh, this is in Microsoft Edge, isn't it? Okay, I can't draw anything on this, but imagine there's a sampling dome placed on the surface of the window, and it looks in each direction. It's Clem's division, so it's going to be 145 directions, and it collects the light from each angle, and then on the other side of the window it retransmits based on the fenestrations you have here. Obviously the light will be the quantity of light will be changed based on the transmission, and the direction of the light will also be changed based on the obstructions you have in there. So so it comes in and it goes through. Now there are a lot of advantages to doing it this way. There are limitations and there are consequences, but there are also advantages. And let's start with the positives. The light is transferred because you've separated this. If you think about it, the light you want to do for your external environment, so that's going to be other buildings, it could be trees, it could foliage, it could be topography. Yes, the rise and fall of the land, like mountains would be an exaggerated example. Think of the scale of that. It is huge, and the shapes can be coarse. Yes, then when you come to the interior section of the calculation, it's much smaller objects. Think about the light bounces here as well. To be honest, we're more interested in obstructions than actually reflected light. It is still important, but the key one is what light from the sun and the sky, from the sun patches and the sky patches to your window, where is it being obstructed? That is the big one. Right, but let's say you need two ambient bounces just to sort of bounce a little bit of light around just to make sure. Now inside here you are going to want significantly more bounces. Let's say 6 to 7 bounces probably for a side lit space. And in addition, think of the sampling accuracy of the space, whereas perhaps out here you need just a very coarse sort of sampling point to look at what light, for collecting light on these surfaces for your ambient bounces. Once you're in here, you want to be looking in a little more detail of how the light is being bounced around the space. If you want to know a little bit more about how radiance is working that out, I did post another video the other week. I think it's called where is radiance sampling points. It's on the channel somewhere. Now, so you've got very coarse, you've got detailed, and then think about when it's passing through the blinds. How detailed does that need to be? You need to make sure that every bit of light that gets trapped in those fenestrations, in those blinds, is accounted for. All the energies. The vast majority of the energy is accounted for. You want a lot of bounces. Let's say 7 bounces. And you want the sampling accuracy to be very tight. So let's say here it's 10 centimeters. Let's say out here it's like a very, very coarse calc. Let's say it's a meter. And inside it's like 1 centimeter accuracy. Now, if you did that as a two-phase calculation all at the same time, it's the you'd have to add up all the ambient bounces. So you've got 2, 7, and so I said 2, 10, and 7. I think I said so. That's 12, 19 ambient bounces. That is an epic calc. That will take a very, very long time. And not only that, think of the accuracy setting. It's the most onerous one that has to be adhered to, and we set a centimeter here. So you are calculating on, like, that's, let's say we built up a small portion of the surrounding architecture, we would be calculating everything to a centimeter. That isn't going to happen. The calculation, well, of course it would happen, but wow, there's no workflow there. It would be like a week's calculation time. So by doing the three-phase method, we can say no. We will, in isolation, we will do our coarse calc, our reasonably detailed calc, and our extra detailed calc when we make our bidirectional scattering distribution function material. Yeah, so we just do it all like that way. So we actually tailor each phase of the calc. There is another advantage as well. Imagine you are doing it could be a hotel rooms or classrooms or pod offices. They are all identical inside, yes, which is very normal, isn't it? Your developer is making a building, and obviously they are just going to repeat the same design across the building. So nothing is changing in here. The only thing that's changing is perhaps out here, there happens to be a tree in closer vicinity, or the floor height has changed, something like that. There's more of an obstruction for that particular room. The only thing that's changed is the exterior. So the three-phase method gives you the opportunity. This is the big calc, by the way. The big one that takes all the time is the interior, particularly if you're doing an actual view, because this here is you don't calculate a view from the window to the sky. Yeah, you sort of collect the data, but you don't do a view. In here you would do a view or your calculation points. Yeah, this is the big calc. So nothing's changed inside, it's all changing on the outside. So all you have to do is recalculate this one, which is reasonably quick, well, relatively quick. Yeah, you just calculate that, and then you just plug the three phases in together, and you get your answers that way. So then when you start to think about it, you have actually quite a fast workflow. You do the big calc once, you already know what your window fenestration type is, and then you say, well, top floor, middle floor, ground floor, east side of the building, west side of the building, and it's much, much more quicker to do that. The other one, of course, is imagine you say, well, what's it like with clear glazing? Now, what's it like with blinds? What is it like if I adjust the blinds? That's really quick to do those calcs as well. You can, if they're pre-calculated, you just plug it all in, and once you have the matrices together to shift it all into annual illuminances, it takes like 20-30 seconds to do that. So you're generating a lot of data, and if you're part of a project team and you're doing these calcs, it gets rid of that frustration that you're kind of like maybe like bottlenecking the project because I can't answer that question without like a significant calculation time. I don't have to bill you any like man hours to do that, but I got to leave my computer running overnight, or I got to lock up my computer while it runs the calc. So this way, it's all quick, because you've done all your calcs in isolation. So those are the positives. It is the opportunity to optimize the calc relative to the area you are simulating, and it is the ability to I can't think of the word, sort of connect different phases, different a different exterior with the same interior, a different fenestration system with the same exterior and interior, without having to recalculate everything. I think that makes sense. So you're saving a lot of time, and there's a lot of benefit. What are the costs? And I did 2 other videos actually, just discussing the 2 major bits. Yeah, oh good, it's here. Okay, the first thing you have to be careful. Well, the first most obvious one is So here's conventional ray tracing. Assume it was that blind, right? See how it has picked up sharply all the blind slats, and you can see that stripy pattern. Look what happens with the three-phase method. The distribution of light around the space, it's pretty much the same. If you look really close, you can see there's small differences, and it depends on the scope of your calc, doesn't it? You know, if you are going for if you're trying to make like a promotional image, it is not acceptable to perhaps, you know, for that level of accuracy. If you're generally trying to understand the quantity of light in the space, particularly, you know, like concept or a developed design stage, not your full technical design, this is fine. This is fine, but just remember that this smooth reduced quantity of light in front of the window is actually an average striping of what's happening here. So as I've just alluded, the reason it is happening is because whereas when you do conventional ray tracing, it is looking at each area and its interaction with the blind. Remember, ray tracing happens backwards. The way it happens with the bidirectional function. Oh, God, I can never remember how to pronounce the damn material. The material here is. Hang on a minute. Let me drink some of my beer. It's warm English beer, lovely. Right. Yeah, so what it actually does is take the average. So it looks at all these slots and that and just basically asks the question, what is the average light distribution from this window? And if you look, the average is basically, it has halved the quantity of light coming through, hasn't it? It has blocked out half. There's full light, no light, full light, no light, full light. The rest of it is just bounce light. And what it's done here is say, well, so the average is 50% transmission through that window. So it has captured the quantity of light coming through the window accurately. It has not accurately captured. It has captured the cutoffs correctly, but it has not captured the intricacies of that window. The other thing you lose is, if you notice, obviously the blind is not modelled. Can you see how the blind is physically in the model? Here it is not, because you just put in a flat thing. Think of it as a light source, actually. You know, like how you have a photometric light source and it describes the light spread from a light fitting. It's the same. It is an IES or an LDT file for a window. So none of it is modelled. It's just flat. But notice you don't get a view through the window either. What you actually start to see is, remember how I said it puts a dome on the window and it looks at what is the quantity of light coming at me straight on? What is the light coming from that sort of hemisphere, or that hemisphere, that hemisphere, and that hemisphere? It's pretty much the same as you know how the whole sky dome is divided into these patches. That's what it's doing here. It's just putting it over the window and it's sampling, and then basically you actually control the accuracy by, you know, do you literally just look in one direction here? Just like what comes from the middle of this point. Wouldn't recommend that. Or what you say is look at 100 different points in that single patch and you take the average. You look at 100 different points and you take the average. Beyond the scope of this video. And and the last limitation of the three phase is you just need to be aware of the way you define it is by materials, and you say, like, you know, if I define a window as my, let's call it glow material, right? Everything of the same material, it will give exactly the same light distribution. And I made a nice video labouring this point. It's pretty good. Just in that, so if you had two windows, but one window was fully obstructed and the other window wasn't, because you define them as the same material, right, it will take the average of the two. So you know how that got averaged? If you took two windows, it would sample both windows, and then on the internal side of it, it would just take the average of both windows, which would be a 50% light output. Imagine this imaginary window here is totally blocked. This one is unblocked. It would just say, oh, this is the average. So what you would do is you have to define them as different materials for their unique sampling. If you're doing it via Honeybee for Grasshopper, or Dynamo if you want to make your life difficult, if you're using Honeybee, what you need, the way that that concept of using the same materials, that's the same as using window groups. So you need to make sure that if you know that both windows are going to be exactly the same in the light they collect, no problem, make them the same window group. If there's a risk that this window may be a little bit more obstructed than that window, and that is important, for my calc, you need to, like, it's called a group, but it would only hold one window. Okay, it's just the way they've decided to do it, and it's a nice, once you get your head around it, it's a bit daunting, but once you start working with it, it's a real nice way to do it. I recommend it. I think that was everything I wanted to say about the three-phase method. Yeah, that's good. So hopefully that slots into the other videos I've previously recorded, and if you choose to, you can just push on to the fourth. I think there's weird sound issues on the fourth one as well. I don't know what was happening, but there's something there. That's good enough. All right. So thank you for listening, and good luck with all that.